Welcome to the second video of Module 3, Topic 1, Simple and Compound Interest. So make sure that you've watched the first video before you watch this second video. So for this video, we're going to continue the conversation about compound interest. So compound interest is the most common type of interest charged in finance and economics. Simple interest is used less often, although certain financial products may contain elements of simple interest. Compound interest is used for money borrowed or invested for extended periods of time. So some examples of compound interest include saving accounts, mortgages, GICs, loans, and RRSPs. To calculate the future value of a loan or investment involving compound interest, we use the future value formula. So we're going to introduce some new variables for this formula and talk a bit about them, as well as obviously do some practice questions. So this formula here that we're going to start with is our future value formula. So we've got some new variables to talk about. The first one is future value. So it is the accumulated value, future amount, maturity value. Not to be mistaken as the maturity value that we were talking about with simple interest. Future value is different, and you're going to see why as we move through the rest of these notes. Present value, so PV is the original principal value, also referred to as present value. Now, this is familiar. We have our R, which is our rate of interest per year expressed as a decimal. So that's nothing new. And we also are going to be using T, which is, again, familiar. It's our time period expressed in years or fractions of a year. So one thing that we are going to see is that our value for present value is going to be in dollars. Our value for present value is going to be in dollars. But we need to speak about rate and T, or R and T, because as you look at the formula for future value, you don't see that. But we do have this I value and this N value, and we're going to talk about that next. So for compound interest questions only, we need values of M, N, and I. So for our M value, that is the number of compounding periods per year. And we're going to talk more about M just in a little bit. Now, N is equal to our M value times T. And this is our total number of compounding periods, entire duration of the loan or investment. So it's not just how much it's being compounded in 1 year, it's how long it's being compounded over the course or the duration of the loan or investment. And then we have an I value, which is equal to our rate, our R value, divided by that M value. And this is what we call our periodic interest rate. And it is interest rate for each compounding period. Okay, so let's talk more about this M value, this compounding period. So this is important because we're talking about compound interest questions. So the time interval between the dates when interest is added to the account is called the compounding period. So this chart below describes some of the more common compounding periods. So we've got some pretty straightforward ones. We've got annually, so that means it's once a year, semi-annually, twice a year, quarterly, 4 times a year, monthly, because there's 12 months, is 12 times a year, weekly, 52, because we have 52 weeks in a year, and then daily, which is 365. So that is if something was compounded daily. Now we have these 3 other ones that can sometimes confuse folks, but semi-annually means that it's being compounded twice a month. So if we have 12 months, we multiply that by 2, then our M value is 24. Now bi-monthly means it's every other month. So if we have 12 months, but we're only compounding it every other month, then our M value is 6. And then bi-weekly also means every other week. So again, we have 52 weeks in the year. So if we do every other week, that means that our M value is 26 if we're given compounding of biweekly. So this chart is extremely helpful. So when you're reading a question, you can look to find what is the compounding period. That is going to be your M value, and you're going to use this chart for your M value. All right, so let's first talk about how we have to calculate I and N first in order to use our formula. So in this example here, it says calculate the periodic interest rate and the total number of compounding periods given the following terms. And we're not going to round our answer. So here we have 11.5% per year compounded semi-annually for 8 years. All right, so we've got our rate, which is 11.5%. But again, remember, we use our rate in decimal form. We see it's compounded, and it's compounded semi-annually, which means twice a year. So if we look at our chart, we'll see that semi-annually is an M value equal to 2. And then we have time, which is our 8 years. So in order to come up with our I value that we need for our formula of future value, we can see that I is equal to our R value divided by M. And if our R value is 0.115 and our M value is 2, we can leave it as a fraction, and often we do because it does not turn into a really nice decimal number, or we can leave the whole decimal value if it's not a really long, ugly, irrational number. So this one works out to a nice decimal number. Now, if we go to calculate N, we know that that's equal to M times T. So again, M is equal to 2, T is equal to 8, so our N value is 16. So in order to use the formula for future value, we need to come up with an I value and an N value first. So in using I or N in further calculation, we have to use the unrounded values. And sometimes that means using it potentially in fractional form. So let's do our first question here. It says, find the amount to which 6,000 will grow if interest is 10% per year compounded quarterly for 5 years. So again, let's highlight what information we have. So we have this 6,000, so that's our present value. We have a rate of 10%. It's compounded quarterly and for 5 years. So we have all the information we need to use our future value formula. So let's take a look at what we have and what we're solving for. So we're solving for our future value. We have that our present value is equal to $6,000. We have our value of 10%, which we know is equivalent to 0.1 as a decimal. Our M value is quarterly, is how it's being compounded. So that means 4 times a year. So our M value is 4. And then our time is 5 years. Okay, so before we get into the formula, we actually have to, again, do that work to solve for our I value, which remember is just R over M, and also our N value, which we'll get to next. So our R value is going to be, our I value is going to be equal to our R value, 0.1, divided by 4. And again, this becomes a nice decimal, so we can leave it as a decimal. And then for our N value, that's going to be equal to M times T. So if M is equal to 4, T is equal to 5, then we get an N value of 20. So we're actually going to use these two values here in our formula. So this is our I value and this is our N value. So let's jump back to our present value formula, or pardon me, our future value formula. Future value is going to be equal to our present value times 1 plus I to the power of n. So above, I introduced this formula, but I didn't talk about it in detail. So we can see our future value is going to be multiplied by everything that's in that bracket. But notice we have now an exponent. So everything in that bracket is to the exponent of n. So when you're putting this into your calculator, be very careful. So our present value we know is 6,000. And it's going to multiply by everything in this bracket, which is just 1 plus our I value. So again, I looked to see what we calculated. That was 0.025. And that whole bracket is going to be to the exponent of n, which we calculated to be 20. When we put this into your calculator, you're definitely going to get a value that likely you're going to need to round. And again, we're talking about money, so we're going to round it to 2 decimals and ensure we include the dollar sign. So our answer is going to be $9,831.70. So sometimes when we get into these financial formulas, the trickiest part for people is just here plugging it into your calculator, making sure that you put it in correctly in order to get the correct answer. And again, we're looking for that future value. So if we know we were initially investing $6,000 and it's being invested for 5 years, we hope that at the end of those 5 years, there's more. And clearly our future value of $9,831.70 is definitely more than what we started with. Okay, so no new variables for this next equation. However, we're taking our original equation for future value and we're just rearranging it to solve for present value. So essentially our initial principle. When you have a future financial goal, like maybe you're trying to plan for a vacation, making a big purchase like a house or maybe a car or even retirement, you might be interested in knowing how much you need to invest today in order to reach that goal of how much money you want in a certain amount of time. So we can rearrange the future value formula in order to solve for our present value. So same variables, just formula is rearranged in order to isolate or solve now for our present value. Let me try that again. So every variable in here is the same as before. We still have our present value, PV, which is the original principal value or present value, our future value, accumulated value, future amount, maturity value, basically how much we want in the future. We have our rate of interest per year, expressed as decimal, and T, time period expressed in years or fractions of a year. And again, similar to before, we have this I value that we need to calculate and then also n. But notice when we rearrange this formula, it's not just the exponent of n, but it's negative n. So we're going to be using a negative exponent as we go into our next set of questions. Now, for some people, they don't like that negative exponent. You can, understanding our exponent rules, maybe from back in 130, that we can remember we could actually rewrite this same formula, but without a negative exponent. And it's the same as simply our future value divided by this 1 plus I to the power of n. So by flipping that bracket with the exponent n to the denominator, it becomes positive. So you could use either one of these formulas. They're the same. It's just different how you plug it into your calculator. Okay, let's do our first question again, remembering that we need to first calculate I and n. We need to see what our m value is in order to calculate our n value. as well as our I value. So similar to our future value formula question, now we're going to use our new formula, which is rearranged for present value. So here's our example here. What principal will amount to $17,715.61 in 6 years if it's invested at 4.5% per year compounded semi-annually? So how much of the accumulated value has been earned by interest? So there's actually two questions to this. This is the second part. So let's tackle first what principal will amount to this future value amount. So what information do we have? Well, we have our future value. So what we're looking for is we want to know how much principal or present value we need in order to get to this future value amount of $7,715.61. So we don't have that present value. We do have our R value, which is 4.5%, which we know is the same as 0.045 as a decimal. Our M value, how often is it compounded? It's compounded semi-annually, which means twice a year. So M is equal to 2 and T is equal to 6 years. Okay, so we remember we first have to solve for our I value, which is R divided by M. So our R value is 0.045, our M value is 2. And again, this works out to a decent decimal number, so we can keep that. And then for N value, it's M times T. So if M is equal to 2, T is equal to 6, we have an N value of 12. So now we've got our value for I and our value for N that we're going to use in our formula. Okay, so we're solving for present value. So my present value formula tells me that it's equal to my future value times 1 plus I to the power of negative N. Or again, you could use that rearranged formula with a positive exponent if you choose. Okay, subbing in. Future value, 17,715.61. And I'm multiplying that by 1 plus my I value, all to the exponent of negative 12. If you put this into your calculator correctly, you're going to get a value that we are going to round to 2 decimal places and ensure that we have our dollar sign. Your final answer should be $13,564.27. All right, so there is the first part of the question, which was what principal will amount to? The principal that will amount to that 17,000 and change is a principal value of, or present value of, $13,564.27. Now, we also have this second question here, which I'm going to highlight again here in pink, where it says, how much of the accumulated value has been earned in interest? Okay, so a very simple additional formula that is important to know is that our interest, or our I value, is going to be equal to our future value minus our present value. So the difference between the two. So if our future value was 17,715.61, and then our present value was 13,564.27, the difference between those two is strictly interest, which is an answer of $4,151.34. So essentially this person, let's say if they did this investment, in interest earned $4,151.34. So not too bad over the course of 6 years. All right, so Next thing we're going to talk about is effective rate of interest. This actually is one of my most favorite formulas because I feel like it can be really helpful when essentially we're comparing different scenarios. For example, different credit cards. Which credit card actually is going to cost me the least amount of money in the end? Or you can look at it as which opportunity is going to make me the most amount of money. But I really like this when I'm comparing credit cards. So, effective rate of interest, what is it? Well, as we know, there's many different financial products available if you're considering borrowing money, like a credit card, a loan, and a line of credit, or investing. Maybe it's a GIC, a bond, a mutual fund, or something else. How do you know which is the best deal when rates and compounding periods can be and are very different? So we have to look at coming up with a way to compare them. So interest rates must be comparable to be useful. So what that means is that both the nominal annual rate R and the compounding frequency, which we know now is M, of a financial product must be disclosed. So compound interest rates are often converted to this effective rate of interest that we're going to talk about, which we kind of refer to as EAR or EAR, as a standard business practice to allow for easy comparison of nominal interest rates. So for any given interest rate and compounding frequency, we can calculate this equivalent sort of rate base on an annual compounding frequency, which is the effective rate of interest. So legislation surrounding lending and credit practices requires the lender to publish the borrower the true cost of borrowing. The most common disclosure is this effective rate of interest. So understanding this and using this in your everyday life is very important. So here is the formula. So our effective rate of interest formula is right here, and it looks a bit more complicated than it really is. We have some familiar variables in here that we used earlier. So you can see that there's two different kinds of brackets here. They're just different brackets. So we've got like these square brackets here and here, and then we've got these more rounded. They're just brackets, and they're just different to sort of make it really clear what is sort of which brackets are nested within the other brackets. Okay, so we've got our EAR, which is our effective annual rate. So that is what we're going to be essentially solving for. We have our R value. We know what that is. That's our rate. We've now talked about our M value, which is our number of compounding periods per year. And we've talked about I, which is our periodic interest rate that we can calculate by taking R and dividing it by M. So let's do an example here for coming up with the effective rate of interest for the following financial products. So our first one here is a loan with an annual interest rate of 12% compounded monthly. All right, so important bits of information here. We have our rate and we have that it's compounded monthly. So what we know is our R value is 0.12 and our M value, if it's compounded monthly, there's 12 months in the year, so M is equal to 12. So from here, we can come up with our I value, which is going to be 0.12 divided by 12, which gives us a decimal of 0.01. So we can use this now in our effective rate of interest formula, or EAR. And remember, I'm going to use the square brackets too, just to help with sort of separating everything that's going on. So it's going to be 1 plus I all to the power of M minus 1. And then we're going to close that square bracket. And then we're going to multiply this all by 100 because we're converting it into a percent. So sometimes I'll even put that percent sign there just to remind people that we're converting it into a percent. So when we plug in our values, so I, we have it as 0.01. Our M value is 12 minus 1. Close that bracket and then multiply everything by 100. We get a rate of 12.68 and change. Let's round this to 1 decimal place. So we get an EAR of 12.7%. Okay, so what this is saying is that even though it's telling us it's a rate of 12%, because of it being compounded, actually in 1 year, you're going to be paying 12.7%. So it's taking in that compounding in order to sort of understand how much is this actually going to cost in the end. All right, now if we look at our next example here, it's a credit card with an annual rate of 18.5% and interest is compounded daily. This is often one of the worst scenarios when we are compounding daily. So every day you're paying interest on how much of a balance you have on your credit card. Okay, so what do we know for this question? Well, we know that R is equal to 0.185. And because it's compounded daily, and there's 365 days in the year, our M value is 365. So our I value is going to be R divided by M. So that's going to be 0.185 divided by 365. So I'm going to leave this example as a fraction because this fraction does not convert into a nice decimal. So I'm actually going to use the whole fraction in my formula because I should not round anything, as we know, until the very end. Okay, so using my effective rate of interest formula, again, just rewriting the whole thing to remind us everything that we are going to be doing for this formula. My first substitution is for I, which again, I'm going to put in the whole fraction for. You can use your fraction key here. You can also just divide, whatever you're most comfortable using. Remember, all of that is to the exponent of 365 minus 1, and then we multiply all of that by 100. So if you've done this correctly with that fraction, you'll get a value that we are going to round again to 1 decimal place. Remember, it's a percentage, similar to above. So we're going to get an answer of 20.3%. So look at this answer. So even though your credit card says, oh, you're only paying a rate of 18.5%, actually with that compounding, especially daily, you're really paying much more than that. You're paying 20.3% on your balance. All right, so this is a great example of showing how when we increase the compounding periods, it in essence increases how much our effective rate of interest is. So if we look at this table here, it says, consider how the number of compounding periods affect the effective rate of interest, which has an even greater impact on higher interest rates. So we're going to determine what is the compounding frequency of each of these different scenarios. Well, the first one is 2.99% per year compounded annually. Well, that means that the effective rate of interest is just the same. And this is 1 compounding frequency, so only being compounded once a year. Quarterly, we know that that is 4 times a year. So even if it's stated as a 2.99% per year compounded, our effective rate of interest actually jumps to 3.02. And if we're looking at a higher interest rate here of like 19.99 compounded per year, notice how it jumps to 21.54. So you start to see that jump when we start to look at scenarios where it's compounding more than just once a year. Our next one is monthly, so that's compounded 12 times a year. So again, it jumps, if initially it was 2.99 per year compounded, the effective rate of interest, jumps to 3.03. Again, not huge because the percent is pretty small to begin with. But if we're looking at a bigger percentage, like 19.99% per year compounded, it jumps to 21.93. And then you can start to see what happens. So if we're compounding even more bi-weekly, so that's every other week, that's 26 times per year. Again, not a huge jump here, but definitely a bigger jump here with a larger percentage to begin with. All right, so that is the end of the lessons for this Module 3, Topic 1 on simple and compound interest. There are some great additional practice questions here. The answers are below, so you can check your work. Highly recommend that you work on these and get used to using the different formulas. So again, remember, we have this effective rate of interest formula right here that we talked about in this video. Going back, we also talked about these two formulas here, where we have the present value formula as well as the future value formula. So those are all part of compound interest. And then prior to that, we looked at our very straightforward simple interest and then our maturity value formula. So again, if you didn't watch that first video, please make sure you go back and do that. And please take a look at these practice questions. Again, you can compare your answers to the answers posted at the bottom of the page.